all of you, again, you can recollect and let me know if anything you have missed out. Okay. So we started the linear delay model, and we told that delay is defined in linear delay model as D equals GH plus P. The unit is tau. Tau happens to be technology dependent, right? P is the parasitic delay, which is a delay of a date when it is driving how much load?
No load.
Zero load.
In zero load condition, the parasitic delay, intrinsic parasitics of a particular gate will be captured by this particular parameter P. H happens to be electrical effort, which is nothing but C out divided by C in. And G is logical effort, and it is dependent upon topology and a bit on technology. For example, as I said, the mu raised to mu p is 2 raised to 1. It is going to be a bit different. If it is 3 raised to 1, it is going to be different, right? So this is how we define the delay. Then we discussed that if there is a multi-stage network, which is mostly in the case you do have multi-stage network, right? Let's say this is the network, right? And here you have a CL, and this is the C in, right? It's a multi-stage network. Then if this gate has a logical effort G1, it has a logical effort G2, though you know the G2 is unity because it's a NOT gate, and it is G3. Then path logical effort will be how much? G1 into G2 into G3. Similarly, path electrical effort will be H equals H1 into H2 into H3, which effectively comes out to be how much? CL divided by
Same.
CN. And I also told you if the circuit has certain branches, for example, again the same NOR gate, because I'm just making sure that it is offering the same capacitance, one NAND gate here, right? So you have one branch here, B1, another branch here, B2. So branch effort will be how much? B1 into B2. B1 happens to be 2, B2 happens to be 2, that is 4, right? In the process, you define one parameter which was also known as path effort. Path effort was how much? F equals G into B into H. Yes or no? This is the path effort. Correct?
Yes, sir.
Now, I told you that our problem happens, the problem here is the problem of optimization, that in what case, how you should be sizing the W by L of this particular NAND gate, W by L of this particular NOT gate, W by L of this particular NOR gate, in such a way that ultimately the delay offered by this particular chain happens to be the least, right? So what was the thumb rule? Thumb rule is every stages. How many number of stages we do have here? 1 stage, 2 stage, and 3 stage. We do have 3 stages, right? 1, 2, 3. So it happens if you want to minimize the delay from this input to this output, then every stage should bear equal effort. You're getting my point? It should be G1 H1 should be equal to G2 S2, and it should be equal to G3 S3, and it should to be equal to some optimal value GH cap. And how did you find it out, this GH cap? This GH cap optimal value happens to be how much? F to the power
1
1
by
by
n.
where n is number of
Stages.
Labels.
number of stages, right? And if it is so, if you have made sure that G1 H1 is equal to G2 S2 equal to G3 S3, then delay will be defined as net delay will be defined as summation of all the delay D1 plus D2 plus D3 plus so on up to Dn. On other word, it comes out to be how much? N into F to the power 1 by n plus sigma parasitic delay of each stages. I equal to 1 to n. Yes or no? Any doubt so far? No doubt, right? Everything is
Sir,
clear? Yeah.
sir, why we multiply the logical effort of different levels?
I'm not getting.
Sir, for overall logical effort, we multiply individual logical effort.
See,
Sir, why?
this is basically we are describing logical effort is a single stage is G1. But when we talk about a path, we are multiplying it like G1, G2, G3. When we talk about a path, this particular thing, electrical effort, again we are multiplying it. It has a region. Region is basically this parameter is basically very important for you. This which is path effort, right or not? Because your problem happens to be to minimize the delay. Yes or no? You want to minimize this parameter G1 H1 plus P1 plus G2 S2 plus P2 plus G3 S3 plus P3, right? You want to minimize this delay. This is the delay of the single stage, delay of the another stage, delay of another stage, right or not? In this case.
Yes, sir.
Now, I told you this happens only if G1 H1, G2 S2, G3 S3 all are equal. Then only you can minimize the delay. Correct?
Yes, sir.
In other words, this happens to be 3 times of GH cap plus P1 plus P2 plus P3. Now, this GH cap, if you might remember, I have derived this relation. It happens to be f to the power 1 by n, where f needs multiplication of all G, all H, and all B. Yes or no? Yes or no?
Yes, sir.
Yes.
So that is why you gave a definition that you know that you are supposed to get in order to have an optimized value of GH cap, you need f to the power 1 by n, and f needs a multiplication of all G, all B, all H. So you decided to give it as a name like path logical effort, path branch effort, path electrical effort. That's it. It is just for your convenience. You getting my point?
Yes, sir.
Right? So far so good. The things were perfectly fine, and you
Sir,
also got to know that delay was minimum. The delay was minimum when each part, when G1 H1 is equal to G2 S2 equal to G3 S3, and the minimum delay was n to the power of f by 1 by n plus summation of all the parasitic delay.
sir, here number of stages n is sir logic gates, na?
Number of stages. For example, you can say this is one logic gate, another logic gate, another logic gate. You're getting my
Okay.
point? Yeah.
Okay.
Now, I also told you that now the question is, yes, I understood one point that delay is minimum, and if it happens like each stage basically gives you f to the power 1 by n effort, right? But the question is, how do I size? I told you either you know Cin or you also know, or these informations are available to you. Cin is also available to you, CL is also available to you. So you start backtracking. You put GH of this stage, G3S3 is supposed to be f to the power 1 by n. This will give you the capacitance value here. Yes or no? This is what we did, backtracking. Because G of this gate is known, is well standard form. H is CL divided by this capacitance. Yes or no? Let's say this capacitance is X, then S3 is G3 into CL divided by X is supposed to be f to the power 1 by n. F is known to you, n is known to you, G3 is known to you. So you will be able to find out this capacitance. Yes or no? We did it last time. Yes or no?
Yes, sir.
Yes, sir.
I told you, now you need to identify the capacitance of this stage. And for this, I told you, due to the branching present here, this sees a capacitance of 2x. Right or not? X because of this one, X because of this one. It happens to be 2x. Yes or no?
Yes, sir.
Right? So it will be again G2S2 is supposed to be up to power 1 by n. You already know what is the value of G2 for an OR gate. That is multiplied by the X2, which is 2x divided by the net capacitance here. Let's say Y. Right? This will give you the value of the Y. After finding out the Y, you want to cross check whether you have made any mistake in the calculation or not. You can simply again backtrack and can get that this capacitance here should be equal to C in. If it is coming at this capacitance equal to C in, means your calculation so far has been correct. So those who has calculated their answers, if they are able to backtrack it rightly, means their approach was good. Later on, they might have committed the mistakes while dividing the capacitances here to NMOSes and PMOSes. They might have done the mistakes here, but up to this point, they will be correct. Understood this particular part?
Yes, sir.
Now, I would ask you one question. Let's say this is the critical path of a circuit, which I need to optimize. This is the input. This is the output. You have a capacitance CL. And you have a capacitance C in. Now, what will be the path effort for this particular circuit? Path effort will be F equals
G.
BH. What if I add one more inverter here? If I add an inverter here, what will happen? Definitely your output becomes output bar. If I add an inverter, output becomes output bar. Yes or no?
Yes, sir.
But let us suppose I'm least interested whether I am getting a true output or a complementary output. I'm least interested. I'm not worried right now. It should be known to me whether I'm getting output or output bar. I'm absolutely fine with that. Then adding an additional inverter, is it changing the F or not changing the F? If I add one more inverter here, I have added an inverter here. Is it changing your F or is it keeping it same?
Same.
Why?
Same.
Why?
The same.
G and B and H are one, sir.
Because G happens to be 1, B happens to be 1, and H is still CL by CM. Right or not? If I add two inverters, then is it still same?
Same.
So can I generalize one statement now? If in a path you are adding inverters, it is not going to change your path effort F. Correct or not? Correct or not? Yes or no?
Yes, sir.
Yes, sir.
That is one point you need to remember, that addition in a particular addition or deletion of any inverters in a particular path is not going to change your F. That is the one point to take. The second point I would ask you right now, if I do have one inverter, this is a load capacitance CL, this is the input capacitance C in, right? And now, and this is, let's say this is my X input, it happens to be X bar. And I do have an alternate same implementation of the circuit like this. But still I will get X bar, yes or no? If
Yes,
it is
sir.
X, will I get X bar?
Yes, sir.
So tell me, which one will be faster from one top? This is topology 1, this is topology 2. If X to X bar, which one is going to be faster? This one or this one? Who is faster?
First one.
First one
Yes, sir.
Yes, sir.
or second one? Tell. First one or second one? Most of you are saying first one. Yes or no?
Yes, sir.
Because first one is having only one inverter. This is having a 3 inverter. Signal is going from here, here, here. And this is, it is going directly here, right? That is why you are saying 1, right? You're
Yes.
saying delay offered by this particular circuit is going to be less compared to the delay offered by this particular circuit. Correct or not?
Yes, sir.
But soon you will be wrong. Soon I will be telling you it is not always true. It totally depends upon the value of load capacitance. I will give you some examples now. So that is one more aspect which we are going to tell you, because you also know that path effort of this one is still same. Path effort of this guy is still equal to H, because G is 1, B is 1. Path effort of this guy is also F equal to H. But, and S totally depends upon CL by CN. Yes or no?
Yes, sir.
And soon you will see the thing which looks very obvious to us, that one inverter is going to give you the least delay. It may be yes, it may not be yes, totally based upon H. That is the electrical effort. That is what load it is driving. Is it driving a small load? Is it driving a moderate load? Or is it driving a bigger load? So soon we will start addressing it. So let me start it now. Now this was the problem I have given you last time. I want all of you to attempt. And for attempting this particular problem, I'm giving you this week. That is still, I can see there is some not a consistency among your answers. So entire batch of MTech and BTech, they need to solve this question. They need to share the responses together. You better make a HDM group among yourself, and you better share your solution of this particular one. And finally, once all of you come to a final one solution, then it means that yes, you have learned from your mistakes wherever you are committing it. Now you are comfortably able to size this particular critical path. Okay, but let me begin with some interesting problem. Can you read this?
Yes, sir.
A control unit generates a signal from a unit size inverter. Let's say this is a control unit, this particular one. The signal must drive unit size loads in each bit slice of a 64-bit data path. Let's say each data path gives you 1 unit of capacitance. Then 64-bit data path will give you 64 unit of capacitance. You're getting my point? The designers can add inverters to buffer the signal to drive the large capacitive load. So can you clearly see the input capacitance happens to be 1 here, and this is a single inverter, and this single inverter is driving 64. Let's say this is 1 picofarad load, this 64 picofarad. You're driving a 64 picofarad load. Or I am saying, assuming polarity of the signal does not matter. Assuming polarity of signal does not matter means if you are giving X, whether you are getting X bar or you are getting X, it doesn't matter to me. Means I'm okay with all kind of polarity. You're getting my point? Then the question is, what is the best number of inverter to add and what delay can be achieved? You're getting my point? I'm saying you have a choice of drivers. You can have one inverter as a driver, and it is the input. It is 1 picofarad capacitance here, and you are directly driving a 64 picofarad load. Then what will be the least amount of delay you can get from this chain? Another one is you are having 2 inverters. You are having 2 inverters, and what could be the least amount of delay you can get? Another one is you are having 3 inverters. Then what is the least delay you can get? Another one is you are having 4 inverters. So can you compare the delay performance? For example, let's say this is my first way of driving load, driving the memory line or any data bus. Another one, this is the second approach, this is the third approach, this is the fourth approach. Now look for the first one. What is the G? For the first approach, what is the G? Capital G.
No, 1.
1. What is the H?
64.
64 by 1.
I am changing. There is no branching. What is the number of stage? N equal to 1. So what will be the least delay? Delay is N into F to the power 1 by N plus sigma P. So how much?
65.
64 plus 1. because the unit inverter will give you P inverter equal to 1. This is the 65, right or not? Look at the second case. What is the G? 1. What is the H? 64. What is the number of stage? 2. Yes or no? Yes or no? Second case, you have two inverters, two number of stages. Yes or no?
Yes, sir.
So what is the delay? 2 into 64 to the power 1 by 2 plus 1 plus 1, 2. How much?
18.
How much?
18.
18. Can you clearly see? This was only single inverter, but these are the two inverters. Are you getting less delay in this case? You never expected it, right or not? You are saying just a time before to me that which one will give you the least delay? You are saying this will give you the least delay compared to this one. Yes or no?
Yes, sir.
But you have seen, even you have to optimize this particular path, even if you optimize this particular path, you will get 65 tau delay, even after the optimization. While if you optimize this path, you are getting 18 tau delay. Isn't it is affected by the H, choice of H? Right or not? Right or not?
No, it is the drivers are affecting the delay.
So,
Pardon?
Number of stages are affected.
Actually, the drivers are affecting the delay.
The important role is basically H. That is the surrounding condition. Surrounding condition is important. If you want to drive a very small capacitance, let's say you could have been driving only 1 unit of capacitance. If you are driving a 1 unit of capacitance, the H could have been 1. If H could have been 1, this could have been the same as F. Then 1 into 1 to power 1 plus 1 could have been 2 times tau delay. Yes or no? Yes or no?
Yes, sir.
Right or not? While H, if this could have been 1, 1, 1, 1, then in this case H could have been still the same. H is 1, right or not? F is 1. Again you could have got how much? 2 number of stages, 2 into F to the power 1 by n. 1 plus 2 tau, that is 4. Are you getting my point?
so what is this numerical value written inside each inverter?
These are the capacitances. After optimization, this is the value of the capacitance. You will get it here in progressive sizing. Can you see?
Okay, sir.
You're getting my point? I'm saying the first, if the capacitance happens to be 64, you told that the very first stage gives you how much delay? 65 tau. The second stage gives you how much? 16 tau. That is the minimum delay you can get. Sorry, 18 tau. That is the minimum delay you are getting. And in order to get the minimum delay, I told you, you have to backtrack and you need to find out what is the capacitance needed. Yes or no?
Yes, sir.
Yes, sir.
These values are achieved after backtracking. You can cross check. For example, this case, what was the F? Sorry, what was the GH cap? For the case number 2, GH cap was how much IUC? 64 to the power 1 by 2. How much? 8?
8.
So GH cap, G happens to be 1. So 1 into H cap happens to be 64 divided by, let's say this capacitance happens to be CX. It is supposed to be 8. Am I getting CX equal to 8? This value? Yes or no? IUC.
Yes, sir.
You're getting this point now?
Yes, sir.
Yeah. So now, can you compare now? I'm giving you the 4 cases. Case number 1, case number 2, case number 3, case number 4. Given in these electrical condition where load capacitance is 64 picofarad and input capacitance is 1 picofarad, can you tell me which one give you the least delay out of these 4 options? Can you do it? Which can give you the least delay?
Third one, sir.
So all of you first find it out. I'm giving the time to all of you. I also want to know the numerical value. So type in the chat box once you are done. Let us see who answer it first from the BTech students or MTech students. All the 4. Please work it out. Once half of the class is done, I will go ahead. Jayant, are you able to understand?
Yes, sir.
Priyal,
Yes, sir.
that's good. Kisan,
Yes, sir.
finding some interest in the electronics or not?
Yes, sir.
So where are you going to join? Electronics, industry, or the software one?
So software one.
Then you can always target the EDA one. No need of going for the data analytics company, right? You can target the Cadence Mentor Graphic, right or not?
Yes.
You are learning a bit of HDM as well. That will help you.
Okay.
You can also target the Qualcomm software profile, right? So let me know if all of you have done. Is there anyone who is not able to understand? Oh, the solution is given now. But still, I want to see how many of you have answered. Third, 15. 15, 15, 15. That's good. Salini. From the BTech students, I am yet to see any reply. Sriyank has replied. That's good. So I think you are able to understand this particular concept, right? So if you see and calculate it, you will identify that this third stage, this was my first, this was second, this was third, this was fourth. Third stage is giving you optimal delay, which is 15. So if your condition is basically like this, you want to drive a 1 picofarad load through an inverter, and it is supposed to drive a 64 picofarad load. Then instead of going for only one inverter, you better go for 3 inverter. Are you able to understand? All of you? You're getting my point? All of you?
Yes, sir.
Yes, sir.
Okay, right? You can clearly see it's the sizing happens in a progressive manner. The unit capacitances here is 16 unit capacitance, here 4 unit capacitance, here 1 unit capacitance. Now 16 unit of capacitance, you will be dividing across NMOS and PMOS. Let's say the mobility ratio happens to be 2:1. You know that if the width here is X, it has to be 2X, right or not? This is the VDD. So 2X into some unit, 2X into some unit of capacitance. This is COX into L. I told you COX into L will be of the order of femtofarad per micrometer, or maybe of the order of picofarad per micrometer. In maybe in your case, has to be equal to how much? 16. So this gives you X equal to 8. Means this should be 8. This should be 16 unit or micrometer. Are you getting my point? You're getting my point?
Sir, what?
That way you can also size this one. Again, 4 unit of the capacitance, 4 into 4 unit of the capacitance. Let's say this happens to be again 4 into, let's say COX into L is 1 picofarad per micrometer. Let's say COX into L is given as 1 picofarad into micrometer. So 4 into 1 picofarad per micrometer should be equal to how much? 4 into W into L, right? You can work it out this calculation, yes or no? Shall I do once more?
Sir,
Yes.
sir, how did these capacitance values are decided?
No, I will tell you. No, I'm taking one case. For example, I'm taking this case right now. Okay. So tell me, for inverter, the sizes need to be of the ratio of X and 2X. Yes or no?
Yes, sir.
This is the VDD. This is the one. What is the net gate capacitance you will get here?
3x.
How much? 3X into COX into L, right or not? See, 3x is the width. Net width happens to be 2x plus x at this capacitance. This is the capacitance, right or not?
Yes, sir.
Cg happens to be cox into w into L. Width here is 2x, here it is x, so 2x plus x happens to be 3x. That is supposed to be, let's say, 16 unit, and let's say your unit is picofarad, 16 picofarad. Now let us assume, or let us suppose the cox into L comes out to be, let's say, 1 picofarad per micrometer. I can say what will be the unit of this capacitance cox? Cox is oxide capacitance per unit area. Its unit will be farad per centimeter square. So I can easily convert it into picofarad per micrometer, right? Per micrometer square. I can
Yes.
convert it to farad per micrometer square as well, right or not? And if I multiply channel length, which is also given in the micrometer, this effective unit happens to be picofarad per micrometer. Yes or no?
Yes, sir.
So now 3x into 1 picofarad per micrometer, and the 3x is also, this is the width happens to be how much? 16 picofarad. So this is in micrometer. So this will cancel each other. So you are getting x equal to how much? Tell me. 16 by 3. Sorry, I think last time I committed a mistake. X happens to be how much? 16 by 3. Roughly how much? Anyone?
So 5.34.
5.34. Then 2x will be how much?
So 10.66.
10.68. That is in micrometer. This is how you will size your W. And length is always, let's say length is already given as some minimum value. For example, in last example, we gave it to 250 nanometer, means 0.25 micron. So you can simply see that this ratio is supposed to be that much. Okay, you are talking about this particular one, and so you know the width is already given here. You can still maintain the ratio, right?
Yes.
So now this is how you will size it, right?
Sir, excuse me.
Sir, I have a question, sir. Sir, how this minimum delay is related to our sir critical path, sir? As we know, sir, critical path is that path which has worst case delay, sir.
That is okay. Critical path, you have the slowest delay, but isn't you would like to make the slowest to be faster for critical inflow? Like if you want to decide the frequency of a particular R2R operation, register to register transfer operation, you know that this is the delay which is impacting my frequency of operation. If you can make this delay less, what will happen?
Yes, sir.
The frequency of operation will be faster. So only those 20% of a path which happens to be very critical of your operation in a microprocessor, you should be worried about the speed. You should not be worried about those 80% paths which are already working fine. You should make sure that these 20% path also work as fast as other 80% path. If you can make it, then you are basically optimizing the operating frequency, or you are reducing the delay of overall circuit. Yes or no?
Yes, sir.
You're getting? Have I answered your question or not?
Yes, yes.
Sir, I have a question.
Mm-hmm.
Sir, when we are doing the 16 picofarad case, there the input capacitance is 16 picofarad. Let's say, for example, the capacitance that is driving is 64 picofarad. So how do we relate it to the other inverter which is having 8 picofarad as input load?
Right. You are saying when you are starting with this input capacitance happens to be 16 picofarad, right?
Okay.
You are saying like this?
No, sir. Yeah, this can also be taken. I want to
You're
compare.
saying 16 picofarad is this one and this is 64, right?
Yes, sir. Yes.
In these cases, these 8 and 4, these will change. They will change, right?
Yes. Yes.
You have to backtrack, and because your H is changed, you have to
Okay.
backtrack and you should get the right value. These values are computed here.
Yes, sir.
Initially, these values are not known to you. These are
Yes.
computed values.
Okay.
If you have this path, then you need to make sure that this happens 23, this happens to 8 capacitance, this happens to this much capacitance.
Okay.
Right?
Yes.
And
Sir.
that capacitance will help you. What should be the WYL of these NMOSes and PMOSes here? What should be the WYL of these here? You are getting my point?
Yes, yes. Sir, actually my doubt is if there is an inverter which has an input capacitance of X and it has to drive a load of say Y, there is another inverter which has an input capacitance of 2X and it has to drive the load of Y capacitance. So how do we compare between these two, sir? What is the delay comparison?
The very simple thing is that what we are trying to say, that you need to get what is the F. Very first thing, you need to find out F, which happens to be not only logical effort but also electrical effort. B into H, I would always call both of them together as electrical effort. Once you have find it out F, now the question is, you are not very sure whether you need to drive one through one, because right now you are doing a kind of hit and trial process, right? You have one inverter here, then you have tried with the 2, then you tried with the 3, then you tried with the 4, and finally from you calculated for this case, 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 and finally you ended up getting case number 3 is best. You are getting?
Yes, sir. Yes.
But slowly, maybe in the next lecture, I will be telling you one algorithm, one way by which you can directly end up that 3 number of stages are the best.
Okay.
So that is going to be the next one.
Okay.
That will help you in determining how many number of stages are the best, because I have already made 2 concepts today. One concept is, in a path, if you are adding additional inverter, it is not going to change your F, right?
Yes.
If you are adding more number of inverter, any X number, N number of inverter in a path, it is not changing your F. Your F happens to be constant, but it is changing your N. For example, if you add 2 inverter in this one, your N changes to 3, while N here is 1. Yes or no? Though your F is same, F of this stage and F of this stage is same. This is still 64. This is also still 64. Where is you are changing? You are changing numbers. N. Yes or no?
Yes.
Your GH optimal is changing. Your GH optimal is changing, right? So what I'm trying to say, adding any number of inverter in a particular path is not going to change your F. And the second, it may be very sometimes it looks to us that one inverter driving a load means this is the best approach, but it is not true. It totally depends upon the surrounding condition. If the load is high, then you, instead of making W by L of this particular inverter very high, because usually students thinks that making W by L equal to infinitely high means current driving capacity will increase very high, right or not? You all say current is proportional to W by L. If you can increase the W by L, what will happen? Current will be higher. If the current will be higher, what will happen to this load? It can charge and discharge very fast. Yes or no? This is our assumption. But as already pointed out by one student in that particular day, if you increase the width, it also increases the
Input capacity.
Capacitance.
So it is not that if you simply increase the W by L, definitely sometime for certain range you will get, if you are increasing the W by L, for certain range you may get certain improvement in delay, but finally it becomes constant, right? And maybe because you cannot do it, like you cannot excessively increase the W by L because it is not going to help you. So it's better to use this approach. It is reducing your delay from 65 of tau to 15 tau. Yes or no? Yes or no?
Yes, sir.
Another observation, if you see, when you are driving this particular inverter, right? When you are driving directly from here, and when you are driving from here, this is going to help you, though number of stages are more, but you are getting almost how much time? 4 times? Almost 4 times improvement in the delay, right or not? What if I could have taken 5 stages, would have got some improvement? If I take the 5 stages, then what will happen? F
Delay
will be
increases.
64 to the power 1 by 5. And net delay could have been 5 into 64 to the power 1 by 5 plus 5. Yes or no? How much you are getting? Anyone?
16.48.
15.48.
16.48.
How much? 15.48 is correct?
16.48, sir.
16.48.
16.48.
So what is it? It tells you you are getting something, some profile like this. For n equal to 1, the delay was 65. I could say like this. N equal to 1, the delay was very high, 64 tau or 65 tau. N equal to 2, you are somewhere here, 1, 2. While n equal to 3, you are at the bottommost. N equal to 4, again the delay has started increasing. N equal to 5, again the delay has started increasing. So this happens to be your least delay. Yes or no? Now next class, as someone pointed out, what will be the way of identifying what should be the optimal size of a chain? Optimal size of a chain, or how many inverters I need to add. We'll be discussing all these kind of things, how to optimize a chain or size of the chain using incorporation of additional inverter in the next class. And we will also get to know what will be the how much additional inverters we can add it up. Okay.